I think where we'd left off at the end of last class was at the overview of organic reactions, and we were just about to start polar reactions. So we'd finished a little section on some radical chemistry, and we were just about to start the polar reactions stuff. Okay, spotlight. Let's move this thing somewhere. Okay, so this is where we're going to link back to what we did at the very start of the term with regard to electronegativity and polar covalent bonds. So most of the organic compounds that we're dealing with are going to be neutral. There's the odd thing which has got it carrying a charge, like say hydroxide, for example. But most of the compounds that we're dealing with are neutral. But they're still going to be involved in polar reactions. So we basically need to know which of the bonds we've drawn are polar. And so this is basically the whole recognizing what's a polar bond, what's not a polar bond. So remember way back when we looked at the families of different functional groups, one of the exercises I basically suggested everyone do was look at each functional group and determine which bonds on the functional group happen to be polar. And so here's just a couple of examples. So if you've got an alcohol, there's technically actually two polar bonds on the alcohol. One which is the polar bond to the proton. So H has got this delta positive, and the other would be the polar bond to carbon. So oxygen's more electronegative than carbon, so this carbon should have a partial positive charge. So there's basically two places where some chemistry can take place. We'll see that the majority of the time it takes place at the proton, but there's going to be a couple of examples later on. We're going to change this slightly where it's going to take place at the carbon. Our friend the carbonyl, this is a polar covalent bond. Oxygen's more electronegative than carbon, so carbon's got the delta plus, oxygen's got the delta minus. And the halogens, this is fluorine or chlorine, certainly more electronegative than carbon. Carbon's got a delta plus. The more electronegative atom will have the delta minus. And the exact reverse is true if you've got an atom which is electropositive, like the lithium. So in this case, carbon's going to be the delta minus. It's going to have the electrons. So methyl lithium compared to methyl chloride, completely opposite chemistry. Okay, so the first thing is being able to recognize which bonds are polar. So perhaps if you've forgotten, review that little section at the start of the term. Now, so there's built-in polarity with any molecule, but there's also things that you can do to a molecule to basically augment the polarity of any given bond. So, and this is particularly true with functional groups that react with solvents or Lewis acids or Lewis bases. So this example here, we're returning to our friend the alcohol. And again, remember, alcohols are interesting molecules. They are both Lewis acids and Lewis bases, depending upon what they are interacting with. So if you've got some acid here, these lone pairs can act as a Lewis base. I'll grab that proton. And now you've got a protonated alcohol. And once this happens, this carbon becomes even more delta positive because the electronegative oxygen is now bearing a formal charge of plus. And so electrons are shifting even more towards the oxygen in this sigma bond. So it becomes a really electron poor carbon. And so this is one method of increasing the reactivity of a carbon bonded to a alcohol is by protonating that alcohol with an acid. So this would be, HA would just be some strong acid here. So that's one example. Another example is what we did with our Lewis base, acid-base reactions before. So boron trifluoride, remember boron's got that empty orbital. Fish tank is making too much noise there. So boron's got this empty p orbital. The ketone will donate its electrons to it. Then we've got a complex. And in this case here, now oxygen's got a formal charge of plus. So because it's bonded to 3 things and has 1 set of lone pairs. So this, once it's complex, this is actually going to increase the polarity of this carbon. It's going to make it, because we can draw a resonance structure where we move these electrons here, and lo and behold, now this carbon's got the positive charge. So this is a way of increasing the polarity of, or the delta plus of that carbon, because you've actually got a valid resonance structure where there is a positive charge of that carbon. So it's harder to draw certain interactions with solvents, but the same thing can happen. And in the next example is what we would call polarizability. And this takes place mainly through interactions with solvents. So remember back at the start, one of the factors that allowed something to become more acidic was, remember, when we were looking at the molecular structure of whatever was bonded to the proton, atomic size was one of the most important factors. So HI compared to HF, HI was a much stronger acid, because once it was deprotonated, that negative charge was basically stabilized in a very large voluminous atomic orbital, because iodine's it's got a much larger orbital than, say, fluorine. So a similar trend happens with regard to an atom's polarizability as you go down the periodic table. So so the electrons in the valence electrons of iodine can be influenced by solvents and external, basically, influences. So it's typically the solvent. And so they can shift around to different places. So and it's really because they are far away from the nucleus, which has got that positive charge. So as you go down the periodic table, these atoms are said to be more polarizable. So iodine's a good example, bromine's another one. If you look at the comparing a carbon iodine bond from a Pauline's electronegativity stuff, you'll notice that they're not very different. I should have a little example of what it actually is, but iodine's electronegativity is actually quite low. But because it's polarizable, it behaves like it is electronegative. So the electrons in this bond tend to shift towards iodine because it's more polarizable. So that basically renders this carbon delta plus. Same thing with bromine to a lesser extent, but all of the halogens, so when you bond them to carbon, in a CF bond, the carbon's got a delta plus because fluorine's so electronegative. With a Cl bond, the carbon's got a delta plus because the chlorine's so electronegative. In a CBr bond, carbon's got a delta plus because bromine is more polarizable. And in a Ci bond, carbon's got a delta plus because iodine is really polarizable. So for all of the halogens, they behave in a similar fashion, but for different reasons. So with fluorine and chlorine, it's because of electronegativity. For iodine and bromine, it's because they're polarizable, because they're lower on the periodic table. So this is the best example of it. So, so you can think of a a carbon iodine bond as a carbon with a delta plus. Yeah, so like solvent molecules, because this iodine's quite large, because remember, every molecule is going to be, particularly when you do reactions in solvents, which we always do, solvents surround these, and that's how they dissolve. And so these electrons can be sort of shifted in a fashion with the solvent to make this carbon a delta plus. Yeah, so this is basically what we're trying to say. I think we use this very same slide when we're talking about acidity. So if you've got fluorine's a small atom, it's electronegative. So that charge is in a small volume and it's not polarizable at all. So if you've got F minus in a solution of H plus, F minus is, because it's localized in a really tiny little volume, there's an electrostatic attraction between the plus and the minus, and they get together and you form HF. So remember, HF was a weak acid compared to HCl, which is a strong acid. We did that in Gen Chem 1. Whereas iodine, this is a really large atom. It's not electronegative, so the electrons are dispersed really far away, but they can be manipulated by the solvents, which makes this thing polarizable. So the negative charge can be stabilized in that large orbital, but it's also polarizable. We're going to see later on that I minus is capable of doing things that F minus is incapable of doing because it's polarizability. All right, so basically the way that this section of the mechanisms were, oh, we got a question. Okay, so, right. So there was a question about how do you know if, for example, fluorine is small and iodine is, say, big. Okay, so the simplest way to figure that out is, and you typically don't go wrong this way, is that if you look, the further you go down the periodic table, the larger the volume is going to be, or the larger the atomic radius is going to be, because basically the electrons are in orbitals that are further and further and further away from the nucleus. So that's the first basic trend, where the further you get away, the size is going to get larger and larger and larger. So the further down the periodic table. Remember, there was trends in the periodic table based upon the effective nuclear charge in Gen Chem 1, where you go from left to right. And as the effective nuclear charge increases, that'll make the volume smaller and smaller and smaller. But for negative charges, remember, a negative charge is always going to increase the volume because you've got an extra electron and compared to the protons in the nucleus, so it's going to expand the radius of a atom. So if you're comparing apples to apples, if we put a minus here, I minus, I's lower on the periodic table, so it's going to be larger. If you had bromine in there, bromine would be smaller than iodine, but bigger than fluorine. So that's basically how the way that that works. Yes. So the next question was, so if the atom is larger, is it more polarizable? Generally speaking, yes. So iodine will be more polarizable than bromine, which would be more polarizable than, say, chlorine. Chlorine is second row. It's really when you get to the third and fourth rows further down. Right. So for what we're talking about, so really it's iodine and bromine are the two ones we'll be talking about the most. So yeah, the next question was about what about atoms left to right? That's really not, if you look at a periodic table, which I should have somewhere, let's look at a periodic table. Okay, so fluorine, chlorine, bromine. Iodine, that's better. Okay, what is right beside fluorine here? Oxygen. And right beneath oxygen is what?
Sulfur.
Right. Okay. And then below sulfur, something we never really hear of too much, selenium. So we don't even know, like this, the atom beside iodine. This is like selenium is pretty. It can be pretty toxic itself. Yeah, Te. So we never are interested in this anyway. So really, when it comes to polarizability, it's really like selenium is certainly would be a polarizable molecule, certainly more than but see, selenium bounded to something. This is what we might perhaps see if you ever did some advanced chemistry, which is well outside this course. Really, the only two things we're worried about is this. When it's going to left to right, all of these atoms on this row really, and maybe even this row, these are not polarizable. These are far less. So it's only really these guys which we have to ever worry about. So it's only basically bromine and iodine which we need to compare to the rest of the stuff. Okay. What's next? Stop this. Okay, so now let's turn on the laser again. So the way that this portion of the class basically works is that opposites are going to attract. So negative, this was our course mantra right at the very start. Negative goes to positive, delta negative goes to negative, delta positive. So negative, of course, is where the electrons are. Positive is where the electrons are missing from. So if you've got a positive charge, maybe something has got, if it's a carbon with a positive charge, it's missing some electrons and it needs to, so negative is always going to be going to positive. So the electron-rich sites are the sites that are negative or delta negative. And that's where the tail of our, so what this little arrow, remember this is the movement of two electrons. What this arrow depicts is that it's starting at the tail and it's going towards where the pointy end is. So the tail is always going to be where the electrons are. So they can be electron lone pairs, or it could be electrons that are in a bond. So what we're going to see is that pi electrons can be at the tail, and even in certain cases, sigma electrons. So think about if we had, draw. We had a little H plus over here. So remember, this is methyl lithium. Remember, this bond is polarized in this direction, and so carbon has got the delta minus. Lithium's the delta plus. So if you were to take some methyl lithium and drop it into a solution which had some H plus in it, what we're going to end up making is CH4, right? We're going to end up making methane. And these electrons that are in this bond are basically carbon's electrons because it's got the delta minus. So these sigma electrons could come in and attack that proton. And whenever you've got, you're using electrons that are in a bond, you always loop the arrow back towards the atom which owned them, so to speak. So it would go like this, as opposed to that, because that's basically looping back towards the lithium. That's so where these electrons are going to start is this arrow. The tail of the arrow is always going to be where electrons happen to be. So it's got to be lone pairs. That's the most common example. Sometimes in pi bonds, and sometimes in sigma bonds, if the bond is polarized, and this is a nice example that I can think of, where carbon is going to use them to attack that proton there to make CH4. So here's basically the general reaction. You've got some electron-rich species, which we call the nucleophile, and you have some electron-poor species called the electrophile. And the pointy end is always going to be directed towards the electrophile, and the tail is going to be starting at the nucleophile. So, and then you would make, in this case, you would make your AB bond. In this case, so in this example here, which I just drawn, the nucleophile would be the carbon with the minus, and the electrophile would be H plus. So it would be, because protons, H plus, it's H with no electrons, it's electron poor, right? So it would be the electrophile. So polar reactions, it's just going to be a series of, we're going to stitch together a bunch of, like sometimes in this reaction here, it's just one step. This attacks that, and you make your product. This attacks that, you make your product. That's not always the way it is. Some reactions have multiple steps associated with them, but in each case, what we're going to be doing is we're going to be stitching together negative to positive, or delta negative to delta positive, that type of thing. It will be hopefully very logical, which is helpful. Oh, let me erase this over here. So nucleophiles. Nucleophiles are, we would call them nucleus loving, I guess would be the, so these are electron rich, and they basically want to donate their electrons. So lone pairs, pi bonds, or sigma bonds, as we said before. And nucleophiles are going to be either neutral or negatively charged. So some examples, if you've got ammonia, nitrogen with a lone pair, water, it's lone pair. So both of these molecules here are neutral, but they can still behave as nucleophiles because they got some lone pairs that they can donate. Lone pairs that they can donate. Our friend iodide here, it's got a negative charge. This is a pretty good nucleophile, a negatively charged nucleophile. And then here, this is neutral. Overall, it's neutral, so methyl lithium. But this sigma bond belongs to the carbon. And remember, if we were to draw this out, if we were to just make this bond polar, ionic, this would be and remember, carbon with the minus was not, carbon has got very little ability to stabilize that negative charge. So it makes it super reactive, a very, very, very strong base. So when carbon is, it is technically a covalent bond. It's not an ionic bond, but this carbon with a delta minus, carbon doesn't want that delta minus at all. So it's a very reactive species overall. So if nucleophiles can be neutral and negatively charged, the electrophiles are going to be neutral or positively charged. And electrophiles, basically, I guess the definition is electron loving. So it's a species that's electron poor, and it can form a bond by accepting an electron pair. So there's a variety of different electrophiles we can think of. So H3O plus is a good example. So some base or nucleophile attacks this proton. These electrons move over to the oxygen, and you'd be generating water, right? But it's still accepting this electron pair. So these electrons are going to move over there. Methyl bromide, similar situation. We've got a polarizable bond to carbon, so delta plus on carbon. Bromine is polarizable, so these electrons will move over to the bromine, or basically a ketone. Polar bond to carbon, oxygen's more electronegative, carbon's got a delta plus. So this carbon is going to be the electrophilic site of this molecule. So nucleophiles have got lone pairs that they can donate, or pi bonds or sigma bonds, but it's electrons in those bonds that are attacking something. And so electrophiles are basically, they're going to accept an electron pair. So we've seen this sort of thing before when we were talking about Lewis acids and Lewis bases, right? It's very, very similar. So nucleophilicity and electrophilicity are very similar to Lewis acids and Lewis bases. So Lewis bases are nucleophiles, Lewis acids would be electrophiles. And just like we had with when we did Lewis acids and bases, some species can be both electrophile, just as some species could be Lewis acids or Lewis bases. Some species could be electrophiles or nucleophiles, depending upon what they're reacted with. So water was the perfect example of a species that could be a Lewis acid or a Lewis base. It's a Lewis acid because it's got a polar bond to H. It's a Lewis base because it's got lone pairs it can donate. So if you put methyl lithium in with it, remember carbon with the minus, it's going to just grab that proton as fast as can be. In this example, it would be acting as an electrophile. Or if it's attacking, say, carbocation, in this case, water would be the nucleophile because it's using its lone pairs to attack that electron poor carbon. So some species can be both, but it depends what it's paired with, I suppose. So nucleophilicity, most nucleophiles are like Lewis bases, and most electrophiles are like Lewis acids. There's some examples, like I guess the technical definition of a Lewis base was you had a lone pair you could donate. Whereas what we're going to see with some nucleophiles is it can be a lone pair, but it also can be as I said, a sigma bond or a pi bond. So that's a ever so slight nuanced difference between the two of them. Let's see here. Okay, so in this reaction here, which species is the nucleophile? All right, so let's see here. Let's draw something. Okay, so we've got carbon with lithium, H, H, H. This is delta minus, this is delta plus. Our carbonyl over here, delta plus, delta minus. And what we've done is, this is a methyl group, so CH3. This is a methyl group, CH3. So what we've done here is we made a bond between carbon and carbon. So if we're drawing our arrows, carbon's using its electrons to make a bond with carbon. And then this carbon over here, the carbonyl carbon has already got 8 electrons. So if we're making a bond, we have to move those other electrons up. The pi electrons in the carbonyl move up to the oxygen. Now we've got 3 lone pairs and a negative charge, and we made this carbon-carbon bond. So the nucleophile is going to be the tail, and the electrophile is going to be, it's going to have the pointy end pointed at it. So the correct response is, I'll stop drawing. Is B. So let's get rid of all of these drawings here. So the nucleophile is going to be the tail end, is going to be where the electrons start the tail, and it's going to attack the electrophile, which is going to be where the pointy end of that first arrow is going to be. Now let me erase these arrows. Clear all. Okay. Let's do the next one. Which species is the electrophile in the following reaction? Okay, let's draw some stuff here. So boron trifluoride is our boron, of course, has got only 3 valence electrons. So when it forms a molecule, when it's with fluorines, it has got an empty p orbital, which makes BF3 a Lewis acid. And so in this reaction, basically our oxygen is going to donate its electrons into that empty p orbital to form our complex over here. And so the tail end, of course, is going to be the nucleophile, and where the arrow is going, this would make BF3 the electrophile. And so the correct answer is B. So B is the electrophile in this case. So boron's got the empty orbital, which makes it a Lewis acid. And remember, electrophiles are very similar to Lewis acids. So electrons are going into that empty orbital. So we would say that this ether would be, when it's donating its lone pairs into that empty orbital, that would be the nucleophile. The nucleus-loving orbitals, electrons on oxygen. Now let me get rid of the drawing here. Good. All right, let's move on to the next. Okay, so here's a little example of a polar reaction when we are using we're going to do a whole chapter on fun stuff with double bonds with alkenes. So ethylene, HBr, when they react, you make bromoethane or ethyl bromide, whatever you'd like to call it. And so 1 + 1 = 1. So this is an addition reaction. And so what we'll see is that addition reactions, and they're sort of given little, so we would call this an electrophilic addition. The HBr is the electrophile in this case, and the ethylene is going to be the nucleophile. So, and this is interesting. So the electrons in this pi bond are going to attack. So HBr, remember, HBr is one of the strongest acids there are. It's a powerful donor of H+. Remember, because Br- bromide can stabilize that negative charge really nicely. So although electronegativity, although when it comes to electronegativity, this, you don't think of necessarily this bond as polarized, but it is polarized because bromine is so polarizable, right? So this is going to come and grab that H plus, and we're going to form bromide. So overall, and then I guess let's go back a step. Overall, what we've done is we've broken this pi bond and we've made a carbon hydrogen sigma bond and a carbon bromine sigma bond. So one of the things that'll be driving this reaction is the fact that you're giving up a weaker pi bond to make two stronger sigma bonds. So that's one of the reasons why this reaction is going to go. This reaction goes super quickly too. So, but this is interesting. So these pi electrons attack H. These electrons move on to bromine, and you end up with a carbon which has got a positive charge. So the ethylene here is the nucleophile. HBr is the electrophile to make this intermediate. And now this carbon is the electrophilic carbon, right? Because it's carbon with a positive charge. And the bromide itself, it is the nucleophile now because it's electron rich and it's got some electrons, so it's got a negative charge. And then again, negative goes to positive. So the tail end here starts at the electrons and it's going to attack this empty orbital on carbon, and that's going to give us our final product, which is bromoethane. So overall, we've made two sigma bonds and we've broken this pi bond over here. But nucleophile, after it's done this initial attack, becomes the electrophile, and before it makes the final product, the electrophile here, HBr, becomes the nucleophile in the second step before you make the final product. So some reactions, there's just one step, like the few that we did in the previous slides, but sometimes there's multiple steps which take place. And it's interesting that what was the nucleophile becomes the electrophile, what was the electrophile becomes the nucleophile before it actually makes the final product. And we're going to see this sort of thing happen over and over again. So the key point here is that all polar reactions take place between an electron-rich site and an electron-poor site. Sometimes they bear an actual charge. Sometimes it's just a polar bond. And it involves a donation of electron pair from a nucleophile to the electrophile. So the tail end starts where the electrons are, and that will be the nucleophile, and the pointy end, the arrow, is going to point towards the electrophile. So it's going to be the delta plus or the full-on positive charge. So this is basically consistent throughout the entire system. So that's how it's always going to work. Now there are basically some rules for there's some rules for using these arrows in polar mechanisms. So the rule number one is basically just what we first start, which we said. The electrons move from the nucleophilic source to the electrophilic sink, we will call it. So they go from the nucleophile to the electrophile. So the key point is that nucleophiles must have available electrons. So lone pairs, oxygen species, nitrogen species, carbon that's bonded to any electropositive atom. So the example we've given the most is lithium, but this could be magnesium. That's another common one we'll see. So carbon with a negative charge, very, very reactive, and that's going to be a nucleophile all the time. And then some of the things that we've seen, which is new, I suppose, is double bonds and triple bonds. So alkenes and alkynes. Now, one of the interesting things that that we're going to see here is that we don't see a similar type of reaction with ketones, for example. These electrophilic reactions that we're going to talk about happen between bonds that aren't polarized themselves. So carbon-carbon double bonds and not really carbon-oxygen double bonds. These have a different chemistry altogether based upon the fact that this bond is polarized in such a fashion and this carbon is electrophilic. So ketones, aldehydes, esters, that sort of thing, they've got an entirely different chemistry because this carbon double bond is polarized, whereas this one, carbon and carbon have got the same electronegativity, so they are not polarized bonds. So their chemistry is very different because they can attack electrophiles, whereas this carbon itself is an electrophile. So there's basically the completely different chemistry here. So let's get rid of that. So we'll see this with alkenes and alkynes in the coming days, I suppose. All right, so that's the first rule. The second rule is that, it's part of the first rule, I guess. This electrophile must be able to accept that lone pair. So it's typically a positive charge, but sometimes, so it could just be a straight up carbocation. It could be BF3, which we used before, which has got an empty orbital. So if it's just got a positive charge and these electrons come in and form a bond, this carbon's got 8 electrons, it's fine. If you've got an example where carbon already has 8 electrons and carbon's got a positive charge and this is attacking, one of those bonds has to break, and it's the bond which is bonded to, which is basically the source of the polarity here. So if this is a Cl, when this nucleophile attacks, the more electronegative chlorine is going to grab those electrons in that bond and depart. So carbon's still going to have its 8 valence electrons. The example with H3O plus, this is a good example. So remember, negative goes to positive. Here, let's draw this out so it's clear. So if we've got let's pretend that we've got hydroxide here. So our rule is that negative goes to positive. You'll notice what we didn't do here is when I drew this arrow here, so this nucleophile is grabbing this proton and these electrons are moving on to the oxygen, which is going to give us water. So this arrow here is going to that positive charge. The nucleophile, which is grabbing this other proton first, then that arrow is grabbing that. We didn't do this because that would give us this, right? Do I have all my electrons? So this oxygen here has got 2, 4, 6, 8, 10 electrons. So this oxygen here would be breaking the octet rule. So negative can still go to positive. It's these electrons here are moving on to that oxygen. So that's, I guess, what I'm trying to say. So this is sometimes a common mistake where you can't break the octet rule. You can still go negative goes to positive, but you don't break the octet rule in doing so. So it grabs that proton, those electrons move there. And then this last example is with the carbonyl. So this carbon's got the delta plus. If the nucleophile attacks there, like the methyl lithium did previously, the pi electrons, because this carbon's already got 2, 4, 6, 8 electrons, those pi electrons are going to move on to the oxygen. So you always want to make sure that the octet rule is filled. So if you're making that bond, you're breaking a bond somewhere else to keep that octet rule. Basically, you don't want to break the octet rule. Okay, so the second rule is that the nucleophile can be negative charged or neutral. So there's lots of examples of negative neutralophiles. We could have said hydroxide. Here we've got a methoxide. And if it's attacking HBr, so this would be just an acid-base reaction. The tails where the lone pairs are, the pointy ends where the delta plus is, negative goes to positive. Once the reaction is over and we've got methanol, you'll notice that it becomes neutral. So what was negatively charged becomes neutral. And then the electrophile itself, the HBr, these electrons, as this oxygen's grabbing that proton, those electrons move on to the bromine. So we generate bromide, and it has a negative charge. So what was negative becomes neutral. And similarly, if you've got a neutral nucleophile, so these pi electrons are attacking the H and HBr. Now, once that's done, this becomes positively charged. So negative nucleophiles become neutral, gosh, it's a tongue twister. Neutral nucleophiles become positively charged. So that's basically rule 2. And what we're going to see is there is a similar rule for electrophiles if they're positively charged or neutral. So that's giving away the next bit of the story here. So electrophiles can be positively charged or neutral. So if they start out as positively charged, so here we've got a ketone that has been protonated. We've polarized this bond even more, this carbon. We've got cyanide. So the carbon lone pairs attack that carbon. These electrons move up. And now our final structure over here is neutral. I drew a little resonance structure with the green arrow to basically say that this is a resonance structure here. And if this carbon attacks this carbon, negative goes to positive. Overall, if the electrophile started out with a positive charge, it ends up being neutral in the end. So that was the key point to that. And if the electrophile is neutral at the start, like HBr, once it gets attacked and this bond is broken, now it's got a negative charge. So electrophiles, if they start neutral, will end up negative. And if a nucleophile starts neutral, like here, it ends up positive. So those are just one of those interesting, and we'll be able, and then this would attack there, and that would be the end of that reaction. And the fourth rule is what I tried to explain before, which is that octet duet rule must be followed at all times. So water attacking HCl grabs these electrons move on to the chlorine and becomes a lone pair. So if the carbon here attacks this carbonyl, this carbon's got 2, 4, 6, 8 electrons. The pi electrons will move up onto the oxygen, and we would have a Now it becomes a lone pair. So we're always going to be maintaining the octet/duet rule. So this hydrogen here, it's already got 2 electrons here. If we're making a bond here, you have to break this bond because it can only hold 2 electrons. So basically, that's the basically the rules here. So you start at the nucleophile, you end at the electrophile, you start where there are lone pairs, or a bond, pi bond or sigma bond, you end, so you end at the electrophile or at the nuclei itself, which has got a positive charge or a delta positive. Or at the end, you can actually become a lone pair. That was this example here. So this arrow goes on to the oxygen to become a lone pair. Yeah, and so there's basically 4 characteristic patterns for mechanisms. The first is what we call nucleophilic attack. So Br minus attacks the electrophile and you form a bond. So lone pair attacks carbocation, form a bond. Now you've got tert butyl bromide. Pi electrons attack the plus nitrogen. These electrons move on to the oxygen, and you're going to make a nitro group on an aromatic ring. Nitrogen's got 2, 4, 6, 8 electrons. So if you're forming a bond between carbon and nitrogen, you have to break one of those other bonds. So this is the first step in the mechanism. We've got to lose this little proton to finish the reaction, but we'll see that a bit later on. So nucleophilic attack, that's the first sort of mechanistic recognition pattern, I suppose. There's a second type of thing which we're going to see, and this is the loss of a leaving group. So if you've got a bond, if you've got an atom which can stabilize a negative charge nicely, like bromine or iodine, there is the possibility, if the conditions are correct around it, which we haven't actually drawn here, that bromine can grab these 2 electrons and just depart. So we would call this loss of a leaving group. So in this case, what we end up with is the carbon which lost those electrons now becomes a positively charged carbocation, and the group which is departed, we call that the leaving group. Now, this doesn't just take place, if we have a bottle of this molecule on the shelf, it's not going to do this by itself. But you can manipulate, if you put this in a reaction and you heat it up with the correct type of solvent, then yes, this can take place. But if it's just sitting on the shelf, this doesn't happen. So although we've just drawn this arrow to say this bromine grabs these electrons and departs as bromide, that just doesn't happen spontaneously without help. Like, we got to do something to make this happen. But this is the type of reaction, or a step in a reaction, so the loss of a leaving group. The third thing is what we've seen throughout the entire acid-base section, which is just basically a proton transfer or protonation, whatever you would call it. So it's just removing H plus from water to, say, this ketone, and this would be some type of equilibrium here. So look where the tail is. The tail's at some lone pairs. Look where the pointy end's at. It's at a polar bond to H, the delta plus part. And if this grabs this proton, these electrons have to move on to the oxygen, and now oxygen's got its 2 lone pairs. If we wanted to go back the other way, lone pair would attack proton. These electrons would move on to the oxygen. So proton transfer, we see this a lot. And then the last one, which is rare, is rearrangements. So this, so here we've got carbon with a positive charge. So these are what we would call carbocations. So it's a carbon with a positive charge. And there was a lot of chemistry done in the early days of organic chemistry with regard to carbocation chemistry. And so textbooks tend to cover this quite a bit in second year. So what chemists have found is that it's possible for, there's that one class of reaction which was basically a rearrangement. There are ways in which the carbon structure can rearrange based upon generating more stable carbocations. So, so basically, and the way that this works is the carbocations basically have different stabilities. So methyl carbocations are the least stable, and a carbon which is bonded to 3 other carbons, which we call tertiary carbon, are the most stable. The more R groups you have, the more stable it is. The more H's you've got, the less stable it is. We'll talk about the stability when we get to the section on substitution reactions. But remember, when we talked about electron donating versus electron withdrawing groups, we did this right at the start of the course. So electronegative atoms were electron withdrawing groups. So if you've got like fluorine or chlorine, they're gonna carbon bonded to a chlorine. This bond is polarized in this direction, and carbon will be delta plus, chlorine will be delta minus. So we've seen a whole bunch of electron withdrawing groups, but what about the groups that were electron donating? One of the groups that was electron donating was carbon. So any, or basically any alkyl group. So alkyl groups are, of course, carbons, right? So anytime you've got an R group which can push electron density, push, 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 the more R groups that are pushing electron density to this positive charge, the more stable it's going to be. So that's one of the factors why a tertiary carbocation is more stable, is because alkyl groups, R groups, donate electron density through sigma bonds. So this is an inductive effect. And so these R groups will be pushing electron density to help stabilize that positive charge. Poor little methyl over here has got no alkyl groups, so it has no inductive stabilization. So that's why it's the least stable. So there's another reason which we'll get to later on in the, but this is just a very sort of general. Alkyl groups donate electron density, so the more alkyl groups you've got, the more stable a carbocation will be. But let's look at an example of a rearrangement and how it works. So let's pretend that you've got a secondary carbocation here. And on the neighboring carbon, you've got 2 methyl groups and a proton. If this proton takes those 2 electrons and hops over here, now this carbon, which it started with, is going to be the one which is missing the proton. So it's going to be a positive charge. So it'll be a carbocation. But it will be a tertiary carbocation because it's got 1, 2, 3 alkyl groups, where before it just had 1, 2. So this will be more stable. This tertiary carbocation will be more stable. If this carbon next door had a methyl group, the methyl group could hop over to put the methyl group here. And this carbon now is electron poor and it's got a positive charge, but it's got 1, 2, 3 alkyl groups, which is stable. Then over here, which has just got 1, 2. So So methyl shifts and hydride shifts are common with when you've got a carbocation. So they've also done some neat stuff, and this is how they help prove that this was actually taking place, is that certain ring structures can expand. I'll give an example of that sometime in the future. But so methyl, these two electrons hop over here. Now this carbon's electron poor. Hydride, so hydride means H with 2 electrons. It's not H plus, it's H minus technically. Hops over here, now it's got a positive charge. So we'll see carbocations when we do substitution reactions, and these sort of shifts do occur in some examples. So the 4 basic types of reactions are nucleophilic attack, negative attacks, positive. You're making a bond between two, like an atom and say a molecule. So you're making this bond. The reverse of that is basically loss of a leaving group. So now the bromine's leaving. So this isn't spontaneous. We have to manipulate it to do this. So that's the exact reverse of a nucleophilic attack, loss of a leaving group. What we did at the start of the class, just acid-base reactions, protons being transferred from one species to another. So that's the third, and the last one's basically rearrangements. This is the rarest of the lot, but we'll see it a bit later on. Okay, so we did that. Okay, so here's a question. Here's the overall reaction which is taking place. This is a click on the target one. So if I was to draw an arrow, oops, what the question's basically asking is, so if we want to draw an arrow to explain what's taken place between this molecule, where's my laser? If we want to draw an arrow to explain what's taking place between this molecule and this molecule to make these two, where does the tail, where does this start? So remember, the tail should be on the nucleophile, or yes. Because the pointy end will be on the electrophile. Let me see if I can add some more seconds here. No, I can't. So actually, now that I think about this, there's actually 2 correct answers, and I think there's only one on the board, which I wrote. But anyway, so what have we, so this nitrogen has got a proton on it. And so if we look at over here, this oxygen's got a negative charge. So we need to protonate the nitrogen. So the nitrogen needs to make a bond with a hydrogen. So this bond here is polarized in such a fashion. So delta minus, delta plus. And so these electrons can be used to attack this proton, which is going to form the bond right here. So the correct, one of the correct answers should be right where these lone pairs are. This is that's what I was looking for. There is actually a second arrow in this mechanism, which goes from here to there, right? Because you're breaking this oxygen-hydrogen bond. Should have thought about that. And so this bond here is going to move on to the oxygen. So if you put that little bond there going to the oxygen, that was technically correct as well. But what I was looking for is this right here. That is where it starts. Right, so this nitrogen lone pair is going to attack that proton. So the other place would have been the little bond in between the hydrogen and the oxygen. Okay, so let's move on to the next question. Okay, so yeah, that was basically the end of the little mechanistic part. So at the start of next class, I'll do a whole bunch of we'll have a little quiz on, well, not really a quiz for anything, just typical sort of stuff that we always do with regards to mechanisms and arrows and that sort of stuff. The second part of the, unless there's questions, the second part of the chapter deals with chemical reactivity. And so the reason why I drew this little diagram, so remember this is a diagram to make molecular orbitals of hydrogen atom with its electron meets hydrogen atom with its electron, and they form a bond to make molecular H2. And why do we do this? Because bond making lowers energy, and if we wanted to break this bond between H2, we'd have to put electrons into the antibonding orbital, so bond breaking requires energy. So if two atoms get together to form a bond, that's going to lower the overall energy of the system, whereas if you want to break a bond, it's going to require energy from the surroundings to break that bond. So the next little part is all about you guys would have done this in Gen Chem 2, I suppose, thermodynamics and all that sort of fun stuff. So there's a little chapter on, little part on enthalpy, entropy, free energy, and that sort of thing. So this is what the next little part's going to be about. Okay, so enthalpy, sometimes we call this the heat of reaction, and it's used to talk about that exchange of energy, which we were just talking about. If you want to break a bond, it requires energy from the surroundings. So, and the amount of energy needed to break a bond, when we calculate this in textbooks, when you've got this enthalpy here, the heat of reaction, it's breaking the bond homolytically. So if you've got a bond between X and Y, X gets an electron, Y gets an electron. Remember, in our polar reactions, we're relying on the electronegativity difference between atoms to break a bond heterolytically. So it's slightly different than what those bond energies are showing here. But if you look at the table in your textbooks for these delta H knots, you'll see that there's some really interesting things. It's like, for example, we did actually, I think we did this at the end of Gen Chem 1. So you've got molecular chlorine, butane or isobutane, and this would be a radical reaction. You make tert butyl chloride and HCl. if you calculate the bond energies, the bond's broken and all this sort of fun stuff, all this math, we would have come up with, so you take the bonds that are broken, you take the bonds that are formed, which one has the most energy, and then you do the math, and it turns out that this delta H was a negative number, so it was an exothermic reaction and a lot of heat would be generated, right? So we did this during Gen Chem 1. Thankfully, we're not really going to do that, any of this going forward, but it's just an illustration of predicting or using the bond energies to see how things are formed. I think this is the question I wanted to look at, because we'll end the class here, and I'll pose a question about, if you look at all these bond energies. So you've got ethanol, the OH bond is 435 kilojoules per mole. If you've got isobutane, the CH bond here is 381 kilojoules per mole. And if you've got like ethane, the bond energy is 410 kilojoules per mole. So the carbon hydrogen bond 410, carbon hydrogen bond 384, oxygen hydrogen bond 435. So think about this little thing before we go to next class, and what looks odd about it. Because I think we're just at 9:50, so class should be ending about now. But this is a good place to stop. So at the start of next class, tell me what's wrong with this picture. Well, it looks odd. And then we'll talk about entropy. And the key part to this section deals with energy diagrams and plotting how what we did mechanistically in the previous part when we were stitching together nucleophiles and electrophiles. I'm trying to get back to when we're stitching together nucleophiles and electrophiles. Those energy diagrams, we're going to be able to put them onto an energy diagram to see which steps should be slow steps, which steps should be relatively quick steps, that type of thing. But that's where we'll stop today. So we'll start off with that question of what looks odd to you. All right. Were there any questions at all? There wasn't really any in the chat, at least none public. Okay, well, what we'll do is we'll see everybody on Thursday then. All right.